Okay, we're going to begin the study of infinite series in detail now. And this section here, we're going to focus on three main types of series. And we're going to start with probably the biggest single type of series that we have, and that's referred to as the geometric series. And they're the ones that look like this. They start at 0, which is a little bit different, and they go off to infinity, and r will be some number, but this will be raised to the k power, so r will be a constant. And you've seen these before, because basically what you're going to have is r to the 0 will be treated as 1, then r squared, r cubed, and that's going to go on forever. So we're going to look at situations where we can actually add this stuff up. So if you remember, s sub 0 then is just r to the 0, which equals 1. Now this piece here, there's a little technical detail I feel it is my duty to warn you about, even though nobody else seems to worry about it. If r is equal to 0, technically speaking, this is an undefined expression. So what some authors have done is they'll write 1 plus a series that starts from 1 to infinity. I am going to defer to the way the books usually do and just treat this number as 1, even if r happens to be 0. So actually, we'll treat it as 0 if r happens to be 0. Sorry, I said that wrong. Anyways, let's take a look at what Sn would be. That would be S0 plus S1 plus S2 plus, well, I'm saying it wrong. This was S1, then 1 plus r is S. This is S0, then 1 plus r is S1, then 1 plus r squared is S2, and now I'm up to S3, and I'll go all the way until I get to r to the n power. So I sort of already showed you the trick that's going to be used here. I'm going to multiply both sides of this equation by 1 minus r. And the left side, I'm going to keep it hanging around for a while. But the right-hand side, this actually multiplies out to 1 minus r to the n plus 1. And then I'm going to divide by 1 minus r. And now we'll take a look and see what happens to these things. So I'll make that n look a little bit better. If r, the absolute value of r, is less than 1, or what you might know is -1 is less than r is less than 1, then this base here is between -1 and 1. What that means is that the limit as n goes to infinity of this piece will equal 0. This equals 1 minus 0 over 1 minus r. So what we have then is that 1 over 1 minus r equals this series it equals sum of the r to the k's when -1 is less than r, which is less than 1. Now, when r is other things, like say when r equals 1, 1 over 1 minus r is not defined. And even if it was, even so, summation k equals 0 to infinity, 1 to the k, equals infinity. You're adding 1 to itself an infinite number of times. So no matter what, this is not going to work for r equals 1. When r is greater than 1, that's also true because these are all going to be bigger than 1 as well. And if 1's going to infinity, these things will even be more. In a similar vein, you can see that r equals -1 will produce an output like this. So we'll get -1 to the k power. Then if you compute your SNs, you're going to see something like s sub 0 will equal 1, s sub 1 will equal 0, s sub 2 will equal 1, s sub 3 will equal 0. You'll get an oscillating sequence of terms, so this will mean that the limit as n goes to infinity of s sub n does not exist. And just as before, when r is less than -1, you'll get a similar situation here, except these will become, you won't have this going on, the numbers will become unbounded. So you'll be able to rewrite it as something like this. You'll be able to do like -1 to the n, but then you'll have the absolute value of r to the n. But now these terms are growing unbounded because since r is less than -1, the absolute value of r is greater than 1, and we're in a situation just like the first one. So this is it right here. The geometric series. You won't believe the stuff we'll be able to do with this one thing. We'll start off with the most basic one. Since I'm starting at 0 and going up to infinity, my r is between -1 and 1. I can go right to the formula, 1 over 1 minus r, and then to simplify. So I get 1 over 2/3, which equals 3/2. All right, my next one, I'm going to start it at 1 instead of starting it at 0. So what you'll have to do then is start it at 0 so that you can use the formula, and then subtract off the situation where k was equal to 0. And so now I can make use of the formula, 1 over 1 minus 0.2 minus 1. This will be 0.8, but then when you flip it, 1 minus 0.2 is 0.8. When you flip it, you'll get 10/8. And then when you subtract 1, you'll get 2/8 or 1/4. Here's another one that doesn't start at 0, so I'll have to start it at 0. So k equals 0 to infinity, 1 over radical 2 to the k, but then I'll subtract off the 0 case. I'll subtract off the 1 case, and then I will subtract off the 2 case. So I'll make use of the formula for this piece. And do the rest of them. I think I'll leave it to you to simplify it. I'm not going to go any further with it there. You get the idea. You can write it as a simpler answer than that if you want to. I guess the first thing that you could do is simplify this by, let me see, we'd have radical 2 minus 1 over radical 2, so this would become radical 2 over radical 2 minus 1. Then you have minus 3/2 minus 1 over radical 2. So I get you started. You can figure out what to do from there. Here I have one that's slightly different. I have now it's equal. It starts at 0 like it should, but up here is not just k. How do I fix that? Well, what I can do is make use of my exponent rules and rewrite that inside as 3/5 to the k times 3/5 to the third. And now, assuming this is going to converge because 3/5 is less than 1, can I factor that stuff out of here? Well, when you think about your SNs, you'd be able to pull that out of every single one of them, so they will survive the limit. And you'll end up with this portion here will end up being 1 over 1 minus 3/5. And then you'll have 3/5 to the third power will be multiplied to that. So I have 5 minus 3 over 5, so it'll be 5 halves times 27 over 125. Not a lot of simplifying can happen here. It looks like we're going to have 27 over 50. K equals 2 to infinity, e to the negative k. At first doesn't look like what we're dealing with because of the negative sign, but once again, I will make use of rules of exponents to rewrite this as 1 over e, that quantity raised to the k power. But now, unfortunately, it doesn't start at 2, so I can rewrite this starting at 0, but I'll subtract off 0, 1, and 2. So k equals 0 to infinity, 1 over e to the k, minus 1 over e to the 0, minus 1 over e to the 1, minus, and I don't have to do any more because I've already taken off. 0 and 1 is all I need to go up to, so that it will take off at 2. So then this portion here I'll use the formula on. And then for these parts I will just evaluate them as they're there. I guess as a common denominator, I guess I would use e minus 1 for everything. E times e minus 1, so it'd be e squared minus e times e minus 1. So that, let's do this again. E squared minus e squared goes away. Negative e times negative 1 will be positive e, but then I have a minus e. So it looks like I'll have 1 over e times e minus 1. That's a nice concise answer. And then for the last type of example, we haven't done any of them that appeal to the negative aspect of the r. So you could have something like this. K equals 1 to infinity, negative 0.3 to the k. And you'll have to do the same thing you did before. Started at 0, k equals 0 to infinity, negative 0.3 to the k, minus when k equals 0, I'll have negative 0.3 to the 0. And then I'll use the formula. So this will be 1 minus, or 1 over 1 minus negative 0.3 minus 1. But let's move on. We can't spend forever on one topic, so I'll have to move on to decimal expansions. And this is another type that you've dealt with a million times. I'll bet you that you know if I have 0.99999 and they all continue on forever, that's actually equal to 1. Let me show you in a bit of a different way why that's true. We have 0.99 going on forever is composed of 0.9 plus 0.09 plus 0.009 plus 0.0009 plus, and this goes on forever. Well, let me rewrite each of these in a way that I can understand. That first one is 9 times 10 to the negative 1 plus 9 times 10 to the negative 2. plus 9 times 10 to the negative 3. All right, so we've got something of a geometric series here. My k, unfortunately, will start at 1 and not at 0. So what we can do then is start it at 0. And then subtract the 0th term. So 10 to the negative 0 will just be 1, so I'll have minus 9 for that piece. For this piece, I'm going to factor the 9 out. As I said, since the series converges, you can bet that I could factor the 9 out of every single Sn term. That's why I'll be able to do it in the series. This is not always something that you can do. We'll discuss that later on. So instead of 10 to the negative k, it's probably easier to think of it as 1/10 to the k. And now it's the geometric series that we know and love. We have 9 times, the series itself is 1 over 1 minus 1/10 minus 9. And then here, 1 minus 1/10 is 9/10, but when I flip it, it'll be 10/9. So I'll be able to flip, subtract, or divide out the 9s. I'll be left with 10 minus 9, and my answer will be 1, which is what I said it would be. I want you to convert 1.9 to 1. I'm putting a bar over just the 2, 1. That means just the 2 1s are repeating. I want you to convert this to a rational number. It means a fraction. We have an integer in the numerator and an integer in the denominator. So let me write this out in some detail so you can see what I'm doing. 21 is, be careful of how long you make this bar. I'm intending that only the 21 is repeating. So this will be 1.9, and then I'll get a series of 2 1s that will go on forever and ever and ever. And now I want to look at each of them. Well, for the one part, I'll take the 1.9 and just tuck it away. But the rest of the other stuff, I want to keep track of. With what you do, the 1.9 I'm going to keep tucked away out there until near the end of the problem. I'll see if I can destroy the 9 so you don't know what it is anymore, but there we go. Now plus this. I'm going to start writing this in an expanded format. I'll have 0.0, 0.021 plus 0. And then I'll have 0.0021. And then I'll have 0.0000021. So I'll have 5 zeros before the 2 1. And that goes on. Now obviously I'm going to factor out a 21. And let me rewrite the rest of these. I'll have 0.001 plus 0.00001 plus 0.0000001. So what are these zeros doing? I got 2 zeros, then I think I messed that up. I would have a total of 3 decimal places for that one. Here I need a total of 5 decimal places, so I'm actually missing a 0 there. And then here I've got 1, 2, 3, 4, 5, 6. I need 7 or 8. Let me see what they're growing by. I've got 2, then I've got 4, and then I need 6 zeros here. And I'll go like that. Now what I'm going to do is I am going to divide by 1,000 out here, because then I can multiply in here by 1,000. I'll get 1 plus, so move the decimal 3 places. 1, 2, 3. And then 1, get rid of 3 decimal places, then I'll have 0.001. So I have 1, 0. Actually, each time I move the decimal place is 3 places. 1, 2, 3, 0, 2, 1. So how many zeros? 1, 0. Then I had 3 zeros. It looks like I'm going to have 5 zeros. And now let me see if I can make sense of this in some sort of a format that involves an infinite series. So it looks to me like we are going to do 0.01 to the k, but k goes from 0 to infinity. That's why I have the 1. Then when k is 2, I'll have that's okay. What I did was fine. When k is 1, I'll have this number. Then when k is 2, I'll get this number. And then when k is 3, I'll get this number, etc., etc. I'm going to change that to something that's more easily doable. Remember, you're supposed to get a rational number, so I'm going to change the 1.9 to 19 over 10. The 21 over 1,000 is fine the way it is, but I am going to change this to 1 over 100. And now I'm ready to use the formula for the geometric series. So that'll be 1 over 1 minus 1 over 100. So you have 19 over 10 plus 21 over 1,000. This part right here will be, down here will be 99 over 100, but if you flip it, you'll get 100 over 99. And then I'll do a little simplifying. The 100 I can cancel with 2 of the zeros there. I can take out a 3, put a 7 up top. So I have 19 over 10 plus 7 over 330. Now if I want to finish the job, I'll multiply the top by 33. So 19 is 627. 7 over 330. That will equal 634 over 330. You can simplify this, although it wasn't required to simplify it. I'll put 317 over 165. So there's how you can go and change a decimal using real math with all the steps counting, all the steps being rigorous and everything like that to get this fraction. So basically this is how you can show, or any repeating decimal you could rewrite as some sort of a rational number. You ought to know that from past math classes. Another major type of series that we deal with is called the telescoping series. I've already done an example with one of these where many of the terms cancel out. Basically what we're doing in this section is we're doing all the series that we can find the sums to, or what that we can actually add up. And then we'll focus on ones that we can't do anything like that with in future sections. So here I'm going to start this at 5, k equals 5 to infinity, and then I'm going to have 1 over radical k minus 1 over radical k plus 3. Now when you look at an Sn, what you're going to see is you're going to have k starting at 5, but it'll be going up to n. So you have 1 over radical 5 minus 1 over radical 8. Don't do any simplifying just yet. Wait till the end of the problem. Then when k equals 2, I'll get k equals 6. I'll get 1 over radical 6 minus 1 over radical 9. The temptation to simplify that has to be terrible, but nonetheless, going on, 1 over radical 7 minus 1 over radical 10 plus 1 over radical 8 minus 1 over radical 11. And it's here that you start to see where things would cancel. If you look, I've got negative 1 over radical 8, but then 3 doors down I have a positive 1 over radical 8, and that's the way it's going to work. This will keep going, of course, until you get to the very last term, which is 1 over radical n minus 1 over radical n plus 3. Now, what I like to do on these things is I like to separate the positives and the negatives. So if you look, the positive terms are going to be 1 over radical k, and they're going to go from 5 to n. So let's put the positive ones in there. I'll have 1 over radical 5 plus 1 over radical 6 plus 1 over radical 7 plus 1 over radical 8 plus 1 over radical 9. And this is going to go on and on and on until I get to 1 over radical n. Now the negative ones are not going to start until you get to negative 1 over radical 8. So I'll put it under there. And then I get a negative 1 over radical 9. Hopefully you'll see that before I get to the end here, the n plus 3, I would have had an n plus 2 before it, an n plus 1 before it, and even an n before it. So it's in this way that I'm going to be able to see what I can cancel and what's left over. So it looks to me that I'm going to be left with s sub n is going to equal 1 over radical 5 plus 1 over radical 6 plus 1 over radical 7, and then minus 1 over radical n plus 1 minus 1 over radical n plus 2 minus 1 over radical n plus 3. And now we're ready to let it go to infinity, n that is. Now for each of these n's, these are easy. The constants, nothing's going to happen to those things. You get 1 over radical 5 plus 1 over radical 6 plus 1 over radical 7. But then these parts will all become 0 because the bottom, the denominator, is growing without bound. And so there's our answer, just these first 3 terms. So the telescoping series are something that we can do. Let me do a couple of hodgepodge problems and to finish this off. So I'll just do a few more examples that'll just be kind of off the cuff. K equals 0 to infinity. I have 1/4 to the k, 5 to the 3 minus k. Now the easiest way to work this is to break this up here. So k equals 0 to infinity. The 1/4 to the k was fine. But then I'll have 5 to the 3rd, and then I'll have 5 to the negative k. The 5 to the 3rd is unaffected by any limiting processes, so I'm going to bring it out front. And now this is 1 over 5 to the k, and this is 1 over 4 to the k. Since they have the same exponent, you can write it as 1 over 20 to the k. And now I can directly use the formula for that because the k starts at 0. And then a little simplifying. Down here I'll get 19 over 20, but I can flip it as 20 over 19. And I don't care if you leave the answer like that. I don't think that 19 goes into the 125 at all. I'm not even going to bother seeing if it does. So I'll just say I have 250 with a 0.2500 divided by 19. Okay, so to work this then, the 3 you don't want to have anywhere inside of here because it's not to the k power, so I'm going to factor out the 3. Now, it's not quite k to the 0. I'm going to do that by taking negative 1/8 to the 3rd power. And of course, then that will be to the k power, because that's one of the rules of exponents with which you are intimately familiar. So 8 to the 3rd is 512, so it looks like I'll have negative 1 over 512 to the k. Now I can almost use my formula, except if I go from 0 to infinity, I'll have to subtract off the 0th term. Don't forget the 3 that's in front of that thing. This I'll use the formula on. I'll get 3 times 1 over 1 minus negative 1 over 512 minus 3 times 1. Notice here that in this case that becomes a positive sign. So I have 3 times 1 over 1 plus 1 over 512 minus 3. Let's see, if I have 513 over 512, so 512 over 513. Just so happens 3 goes into 513. If you've ever done this trick, and you add up the digits, 5 plus 1 is 6, but plus 3 is 9, then you know both 3 and 9 go into the number. How many times does it go in? I believe it's 171. And so I'll get 512 over 171 minus, now if I make this over 171, well, I'll just reverse what I just did. And it looks like I'll have negative 1 over 171. And for my last example, now these also, it's nice to use this trick with the natural logarithm. Since both k's are going to be positive, I can break this up. And I don't know why that came about, but let's change this to k equals 1 to infinity ln of k plus 1 minus ln of k. So you can see this is a telescoping series. All the other terms are going to cancel out. So when you look at your, so I don't have to worry about starting at 0. Telescoping series is its own game. So let me look at Sn. If I look at that, I'll start the positive ones with ln of 2, then ln of 3, all the way till ln of n plus 1. So I'll get ln of 2 plus ln of 3 plus ln of 4, ln of 5 plus, and then I'll finally end at ln of n plus 1. And I'll subtract off these, and they'll start at ln of 0, ln of 1, sorry. And they will end at negative ln of n. So I probably should have put that in here, as it will cancel out, but let's go ahead and get rid of all these things in between. Ln of 1 is just 0, so we just end up with ln of n plus 1. Well, the natural log of something going to infinity does go to infinity. Even though it's slow, we know that the limit as n goes to infinity of Sn equals infinity. So the series is divergent.